The next test we're going to get into comes from section 13.1, right? And this one describes the this test called Anova, which is an acronym that stands for the analysis of variance. But you will be using a new table. This is table 8. And in this table, you can see that this is called the F distribution. And all of these numbers in here are critical values that you can identify if you're going to use the classical approach. And there is a classical approach to this one. There are two different kinds of degrees of freedom, however. This is the only test that we've used where there's a degrees of freedom in the numerator. So we'll call it df sub n. And then along here, there's the degrees of freedom in the denominator. So you're going to have a fraction, and the fraction is going to have a numerator and a denominator, and there's a different degrees of freedom for each one. And so you have to match the degrees of freedom in the numerator with the degrees of freedom in the denominator. And then the alphas, so here's your area in the right tail, this is your alpha. The alphas come in groups of 5, and they list the most common alphas that we use. I think there are 4 different sheets for this table that correspond to the different degrees of freedom in the numerator, degrees of freedom in the denominator. So we'll keep this off to the side, and we will refer to it at the appropriate time. Okay, here's the notes that you should have. And this is the this test is the one that we use. If you just want to make a hypothesis test or a claim about one mean, then we're going to be using the procedures from 10.3. Our null hypothesis would be something like this: mu equals 14, or mu equals sub mu 0 value. If you had 2 means, we would refer to section 11.3, and you'd have something like mu 1 equals mu 2 as your null hypothesis. When you have 3 or more means, that's when you're going to use this analysis of variance. And the null hypothesis here is just going to be mu 1 is equal to mu 2 is equal to mu 3. If you have 3 groups, if you have more, then you can just add on mu 4, mu 5, and so on. Now this test is not, it's going to tell us if there's a difference in the means, but it's not going to specify if there is a difference where that difference exists. So we're going to have to read the sample results to find out where the difference exists. So it'll say that there is a difference, it just won't tell you what difference it is. So here's another test that it works only with means. If you have a problem with multiple proportions, you got to go back to chapter 12, 12.2. And here are how the hypotheses are going to be written. Very similar to that example that we did before. But instead of P1 equals P2 equals P3, we have mu's because these are the variables that we use for means. The alternative hypothesis to negate the null hypothesis. What negates that they're all equal? Well, to negate that they're all equal, all you need is one mean that's different. You could have 2 of these to be exactly the same, but if the third one is different, then you negate the null hypothesis. So the question for us, if we have 3 groups, is that does every distribution look like this? One on top of each other, where all the means are right in the middle? Or do the three means look like this? Whereas one mean is less than a second mean, less than a third mean, something like this. The other way that we'll look at, again, we're dealing with means here, so we're going to be using numerical data. The other thing we'll look at will be box plots. So here you can see there's not a lot of difference between these three groups. If generally in a box plot, this is the median, but if we just say that it's the mean, and this is mu1, mu2, and mu3, they're all fairly close together. This test takes into consideration not only the position of the means, but also the spread in the data, the variances or the standard deviations. All right, this little piece here basically says, well, why shouldn't we just, if we wanted to know if there was a difference between three means, why don't you just pair them up and do a t-test? Do a t-test with mu1 and mu2, do a t-test with mu1 and mu3, and then do a third t-test with mu2 and mu3. And the problem is when you do so many tests like that, your probability of making a type 1 error increases. Here we're only doing one test. And so the alpha of 0.05 really is the alpha of 0.05. What's required? Well, we have to have three different independent groups. And from each group, we're going to take a sample. And K equals the number of groups. So you'll need to identify that number. These are independent groups. Each one of these populations is normally distributed. And we're also going to assume that the three groups have the same variance, same standard deviation. And there's a test down here, or some information down here to say how you can check for that. N1 will be the sample size of the first group. N2 will be the sample size of the second group. And N3 will be the sample size of the third group. You'll be asked to calculate the pooled sample size, the overall sample size, just N. And that comes from just adding the sample sizes of the three groups. And again, if there was a fourth group, then you just tack on plus N4 here. Now, while we're here, the degrees of freedom in the numerator is a calculation that uses these numbers. Degrees of freedom in the numerator is K, the number of groups, minus 1. And the degrees of freedom in the denominator is equal to this N, this overall sample size, minus K, the number of groups. So if you add these two, you'll get N minus 1, which is the degrees of freedom if you have a bigger size, for the two sample t-test, or the t-test with one mean. And here's kind of a test just to make sure that this condition is met. That is, the populations must have the same variance. How do you verify that? Well, this procedure can be used if the largest sample standard deviation is no more than twice the smallest. Remember, standard deviations are the square root of the variance. So as long as they're close in size, you can run this test. Okay, so there's this test statistic that we do have a calculator function for it, and it's called Anova. And the way that this test works in with the calculator is that you have to actually enter data into L1 and L2 and L3. And then when you run the Anova, you don't have a special menu where you go and enter things. You just say Anova, L1, comma, L2, comma, L3, comma, and then run the test, and then it calculates the F test statistic and the p-value. So it gives you those two numbers. It also gives you a lot of other calculations. Here's the test statistic. Between sample variability, within sample variability. So this is the numerator of the fraction, and this is the denominator. We're going to call this the mean square treatment divided by the mean square error. So you're going to see these variables. And these are like variances, and we're going to take, and the reason it's called the analysis of variance is because to calculate this test statistic, we're actually going to be using some variances. And the mean squared treatment is the sum of squares of the treatment groups between groups, and then the sum of squares within groups. Oops. Mean square error. All right. Divided by the degrees of freedom in the numerator, and then the sum of squares of the error divided by the degrees of freedom in the denominator. And we've calculated these. The hard calculations are these here because these are variances, and for each data value, you have to subtract it from the mean, divide by, and then sum up all those differences, and then divide by the sample size -1. So they're variances, and the calculations are very tedious, and that's why we allow the calculator to do that. All right, so your box plots look like this. If they look like this, then you can expect to see a significant differences between mu1 and mu2 and mu3. If the box plots look like this, where all of these, looks like the variances are about the same, but the means are different, then you won't get a statistically significant result. And I thought this was going to look better, but it doesn't quite. Here are the two situations. You have the means are the same. Mu1, mu2, and mu3 are always the same. But this data here spans between 4 and 6. So it's like this one here, between 4 and 6. And this one, first value of this group here falls between 7 and 9. And so what they're doing is just plotting these values over here. And then the third group is shifted completely larger, and it ranges from data values from 10 to 13. And the mean is right here at 11. So this picture here would look like this, and these box plots are shifted quite a ways apart from one another. Whereas this one here, and you can't really see it here, but you've got this mean of the y's, and so here the mean is 5, but it comes from taking values from 0 to 14. Here's the mean. So this would be the box. Let's say, well, it's not the box, but this is the range of the data. So it's a big range. And then here's the mean, and these data values span between 3 and 15. So from here to here. Again, a big variance, big standard deviation, big range there. And the third group goes from 6 to 15. So this one right here goes from 6 to 15. There's a big standard deviation on each one of these and a very small standard deviation up here. If you see something like this, then the box plots will look like this, and there will be a statistically significant difference in the means. Whereas here, same means, but you got much more spread in the data for each of these. And if you see a picture like this, then there's not going to be a statistically significant difference among the means. Okay, a lot of the rest of this, you know, the way that we determine the p-value and so on is there is a classical approach, and we'll base the decision on the p-value. And this tells you how to use your calculator. Type this in already. So let's go through an example so you can see how this works. And the example we're going to look at on this handout is the soybean yields. So for this test, you're generally going to start by entering in data into 3 lists like this. All right, so the question is, you know, they're always looking for ways to make plants grow better. So the number of pods, okay, pods in soybeans would be, I'm not going to be able to draw it here, but here's your plant. And you got kind of some leaves and, all right, and then you have these little like peas in a pod, but they're soybeans in a pod. And you know, how many of these guys? You would hope with the ground that you're using and the water that it receives and the fertilizer that it receives, all of those things contribute to the number of these little pods that you see. All right. A random sample of soybean plants for various types. So this is the plot type. You got the Liberty plot type, the no-till plot type, and the chisel plowed plot type. And it looks like we had 1, 2, 3, 4, 5, 6, 7, 8, 9 plants in each of these 3 plot types. And then they counted up the number of these little pods in each one. All right, so from what you observe in the data, do you think that there's a difference? I mean, should this farmer go only to Liberty plots? Or should they go to only no-till plots or only to chisel plowed plots? Is one of these different plot types, does it yield more of these pods? All right, so this is the kind of data that they use.